So I'm Dafina Xhako from Albania. I represent the Polytechnic University of Tirana. First, let me thank you for this very nice organization of this conference, which give opportunity for different peoples abroad the world to represent their works, their research and their perspective in science. In my case, my paper is a little bit, let's say, different from what I have heard still now. I will represent a paper or a work done in computational physics, in a specific way in lattice quantum chromodynamics calculations. The paper is titled Setting the Lattice Space in Lattice QCD using QCDLAB2, which is a kind of special software. I want to thank the Albanian Association of Medical Physics, which it's a partner in this work, and I am also co-founder of this association, and also my institution where I work, let's say, full-time as a researcher and professor, which is Polytechnic University of Tirana and the Department of Physics Engineering. Also, all this work is done in memoriam of Professor Artan Borici, who died from the pandemic since a year ago approximately. My talk, briefly, it is has this let's say outlines. First, the motivation, why we do such kind of research, of calculations, etc. And a short introduction to lattice QCD, and then how we calculate interquark potential with this kind of special software, which is called QCDLAB2, and then the lattice space, that is our main objective of this paper. How is derived from quark-antiquark potential, and then the conclusions. So the basic motivation of our work is, as I say before, how can we study the physics of strong interaction, the theory that study the strong interaction between particles. And one way that we can study this theory in low energy regime is lattice QCD. So, but we have to take into account that the physics of strong interaction is based on spontaneous chiral symmetry breaking, and this theory in low energy regimes can be studied only with numerical simulations of the quantum theory of interacting quarks as gluons. This theory is formulated in an Euclidean four-dimensional finite and regular lattice with periodic boundary conditions. And in lattice QCD simulation, the formulation of the theory should be chiral in lattice, in order that symmetrically breaking happens dynamically from interaction then. And this is the main motivation why we have to do lattice simulation with chiral terminals. A short introduction to quantum chromodynamics is the theory of strong interaction, as I said before, between quarks and gluons, where quarks are defined as spinor fields, which have color, spin, and flavor, and then gluons are defined as gauge fields, which have color and spin. It is a theory which is based on the SU3 local gauge invariance group, and it's complex because of the gluon-gluon interaction, so it's a non-linear theory, and is characterized by two important features, the asymptotic freedom and the quark confinement. The quantum chromodynamics can be studied in two levels of energy. In high energy scale, we have experimental QCD that we know. So just to accelerate a little bit my presentations, and in low energy scale, which is our case of study, is the Lattice QCD, which is of the range of 1 GeV. We have strong coupling, so the perturbative methods can be applied to solve this theory. It is based on discretization of space-time in a hypercubic lattice with n-node pair direction, which are separated by a distance a. And the fields that represent the quarks are defined on lattice sides, and the gluon fields are defined on the links connecting the neighboring sides. In this level shows the one important feature, which is called the quarks confinement. So the quarks are confined within the hadrons, so we can divide them. And this theory in this regime can be solved numerically with Monte Carlo simulations. Shortly, the Lattice QCD discretize the space and time in such a way that we have such input parameters of the lattice. We have the sides per dimensions, we have the light quark mass, and the value of bare coupling. And then after we done our calculation simulations for a specific, let's say, physical quantity, we have and we must take the limits, such as continuum limit, which the parameter a goes to 0. The infinite volume limit is the case when the distance length goes to infinite, and the chiral limit is the case when the mass of the quarks goes to 0. This approach to solve this theory, so the Lattice QCD approach that says, has advantages and there are disadvantages. As advantages, this theory is finite degree of freedom. It has finite degree of freedom because the physics quantity can be calculated numerically with Monte Carlo simulations. Can study features of QCD that are impossible to study in experimental QCD, such as quark confinement. And the action here is invariant under gauge transformation. Regarding these disadvantages of this approach to solve the quantum chromodynamics theory, so the Lattice QCD, is the fact that this way to solve this theory introduce discretization errors of the range of a square, and the finite size effects, and the Monte Carlo method also introduce statistical errors. A major work is done to build or to construct, let's say, a soft that is dedicated to this kind of simulation. Is a special package software which is dedicated for Lattice QCD algorithms, and it's introduced by our honored professor Borici. It is a collection of MATLAB function, and it is based on small codes that are run in minutes, so are fast codes. First, we have tested the QCDLAB version 1, and we have developed in this version, which is a two-dimension version, a fast algorithm to simulate chiral fermions in Lattice QCD. And then we have, after we saw our results, and then we, from this good result that we have taken with QCDLAB1, then we bring now the QCDLAB2 and our calculation about interquark potential. QCDLAB2, in difference from the QCDLAB1, is the same philosophy, but the set of programs here is written for configuration in the SU3 theory, so in 4 dimensions. The interquark potential, it is derived from QCDLAB2 in this way. First, we have to calculate the quark-antiquark potential, but that are derived from Wilson loops. Wilson loops can be calculating directly with simulations in Lattice QCD. And then we construct the potential with this formula here. And for each R, that is the spatial dimension, we select effective potential when the long time t is reached the plateau. And the calculated quark-antiquark potential values in Lattice are modeled as this formula here in, let's say, in physical unit. And the Lattice unit is the formula here. After that, to take the physical quantity in continuum, we have to repeat simulation for different lattice volumes, and then taking physical length constant, approximately 1.6 femtometer, and then to extrapolate in the continuum limit where A, so the lattice space parameter, goes to 0. We have done the work in such steps. That says we have calculated the string tension K repeating simulation for 100 different configurations for different lattice sizes, volumes. The results that are taken are fitted with the equation above here. And then the R was chosen for fit between 0.5 and 8, and we have done all simulation using Wilson action for these different lattices volumes using the QCDLAB2 soft. And below I will represent the graphical results. The figure 1 represents the graphical representation of quark-antiquark potential in lattice volume 8.4 in a gauge field background with 5.7 coupling constants in lattice unit. As we see here, the full line represents our calculation, and the dot lines represent the range of errors that are calculated with jackknife methods. And as we see, for short distances here, we have a rise of potential as 1 divided by r, that is distance, proportional. And then for large distances, we see that this potential is proportional to the distance r. The same is with a larger lattice volume and with the third lattice volume. We have also a table that represents all calculations and the calculated lattice space A and the string tension and their respective statistical errors for different lattices volumes. And if we, for example, want to know and to calculate the parameter of the lattice A for one specific lattice volume, for example, for 8.4, we have the results for this volume, and then with this parameter we can convert all lattice unit quantity in physical unit quantity. So the conclusions briefly: studying and calculating the interquark potential in the pure gauge theory serves to determine the scale of theory from which all the other calculated quantity in the lattice can then be converted into physical quantity. The results are of calculation of interquark potential with QCDLAB2 confirms the fact that the quarks are confined into hadrons. So the form or the shape of the quark-antiquark potential confirms this fact. And also, we are very optimistic that QCDLAB2 is a set of codes very efficient in lattice QCD simulation, also in SU3 gauge field. And motivated by these results in our future work, we have to develop inversion algorithms for chiral fermions in 4 dimensions, so in SU3 gauge theory, using its environment QCDLAB2. All this work is done as acknowledgement to my professor, as I said before, and also it's done in the serves in the parallel system of the Faculty of Information Technology and the Department of Engineering Physics in the Faculty of Engineering Mathematics and Engineering Physics in the Polytechnic University of Tirana in Albania. Thank you very much, and apologize for my maybe English not so clear and perfect but anyway, I want to thank you for this opportunity. Thank you.